Hello everyone, and welcome to Jam Academy. In this lesson, we want to calculate the work done by a stretch or compressed spring. Now, this is a very good example to demonstrate a force that is position dependent. And I just want to use this moment to show you how to calculate the work done by a variable force. Now, if you compress an elastic spring and let go, what happens? It springs back to its original position. Now, almost every elastic spring obeys a simple law called Hooke's law. Now, in accordance with Hooke's law, the force that the spring exerts is proportional to its compression or extension, but oppositely directed to its compression or extension. In other words, the spring force is proportional to negative x. The negative sign is to indicate that the direction of compression or extension is opposite to the direction of the spring force. So this means that the spring force Fs is equal to negative kx. Clearly, you can see that the spring force is position dependent. Now, the next task will be for us to calculate the work done by the spring. This, my friend, is simply called Hooke's law. Hooke's law. And the constant K is a positive constant known as the spring constant. Now, the spring constant is a measure of the stiffness of the spring. Let me break it down for you. Now, if the spring constant is large, it will be very difficult to stretch or compress the spring. We say that the spring is hard. But if the spring constant is small, it will be very easy for you to stretch or compress the spring. That is why I have defined the constant K, also known as the force constant, as a measure of the stiffness of the spring. Now, to give you an experimental definition, K represents the force per unit length required to stretch the spring by a unit length. Let me say that again. K is simply the force required to stretch the spring by a unit length. And that's pretty straightforward. So the work done by the spring, W, is defined as the integral of Fs dx. Let me put it that way. I'm going to integrate from x initial to x final. So this is equal to the integral of negative kx dx from x initial to x final. I can take the negative k outside, and this will be the integral from x initial to x final of x dx. Now, this would mean that the work done by the spring is equal to negative kx squared over 2 from x initial to x final. And if we simplify, this is equal to negative k bracket x final square over 2 minus x initial square over 2. So this represents the work required to stretch or compress the spring. The work required to stretch or compress the spring. Now, if x initial is 0 and x final is x, this would mean that the work done will be equal to negative k bracket x square over 2 minus 0 square over 2 which is equal to negative 1/2 kx squared. This is the work done by the spring. Now, if you notice, the work done by the spring is negative. Why is it negative? It's negative because the work is done by the system, which means that the system loses energy. In other words, the energy content of the system decreases. That explains why the work done is negative. But the work done on the spring by the external agent pushing on the block is positive because energy is added onto the system. It's important you know the difference. Thank you so much, fellas. If you have any question, please do not hesitate to ask in the discussion forum below. Thank you, and bye-bye.